Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the area of square ABCD, and in the second question, we'll find out the value of the green shape. Okay, let's start with the first question. In the drawing, we have a square ABCD. Inside the square, we have this circle, and we also know that angle CBT equals to 30 degrees, line segment PD equals to 5 units, and our mission is to find out the area of this square ABCD. Okay, so first of all, we'll define the center of this circle as point O. We will join points O and Q together by a straight line. Point O is the center of the circle, point Q is the point of the circle itself, therefore OQ is the radius of the circle that we define as R. OQ equals to R. And we have the radius OQ that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees and this angle will also equal to 90 degrees. Likewise, we'll join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of the circle that is equal to R. And again, we have the radius OP that is drawn to the point of tendency, therefore according to rule number 1, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. We also know that all the angles inside a square are right angles, so this angle is equal to 90 degrees. This angle will be also equal to 90 degrees. This angle equals to 90 degrees. And finally, this angle will be equal to 90 degrees. So inside quadrilateral POAQ, inside this quadrilateral, we have 1, 2, 3 right angles. And the sum of 3 right angles is 270 degrees, plus the size of the fourth angle. In total, the sum of the fourth angle must be equal to 360 degrees. So this angle must be also equal to 90 degrees in order to complete the sum of the angles in quadrilateral QAPO to 360 degrees. This angle must be equal to 90 degrees, because 270 degrees plus 90 degrees is 360 degrees. That is the sum of the angles in any quadrilateral. Okay, so found out that inside quadrilateral AQPO we have 4 right angles. So quadrilateral AQPO that has 4 right angles is a rectangle. Okay, quadrilateral AQPO is a rectangle because it has 4 right angles. And we also know that the opposite sides of a rectangle are equal to each other. That is to say, PO equals to AQ. PO equals to AQ. Okay, PO equals to AQ. But we know that PO equals to R, it is the radius of the circle. So here PO equals to R. From this equation, R equals to PO equals to AQ, we will derive that AQ is also equals to R. AQ equals to R. Okay. Here we can write down that AQ equals to R. Likewise, according to the sum rule, we get that QO equals to AP. QO equals to AP. But we know that QO equals to R, it is the radius of the circle, so we can write here that QO equals to R. And from this equation, R equals to OQ equals to AP, we will derive that AP is also equals to R. AP equals to R. Okay, here AP equals to R. So we actually found out that quadrilateral AQPO is not a rectangle but a square because of the fact that all of its sides are equal to each other, they are equal to R. So quadrilateral AQPO is a square. And because of the fact that ABCD is a square, all of its sides are equal to each other. That is to say, AP, side AD, this side AD equals to side AB. AD equals to AB. AD equals to AB. In square ABCD, AD equals to AB. Okay? AD equals to AB. What is the value of AD? AD equals to R plus 5. AD equals to R plus 5. And what is the value of AB? AB equals to R plus QB. AB equals to R plus QB. So here we got that R plus 5 equals to R plus QB. Here we will subtract R from this equation, equation number 1, and we get that according to equation number 1, R equals to QB. So QB equals to R. Here we subtract R from this equation, equation number 1, so R will get cancelled. And we get that QB equals to 5. QB equals to 5 according to equation number 1. So we found out that QB equals to 5 units. QB equals to 5 units. In the next step, we will implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common extreme point to a circle are equal. We have the common extreme point, point P. From the common extreme point, point P, we have two tangents to the circle, tangent PA and tangent PB. And according to this rule number 2, PA equals to PB. So we actually implement rule number 2 in our drawing. We have the common extreme point, point B. From the common extreme point, point B, we have two tangents to this circle. We have tangent BQ and we have tangent BS. And according to rule number 2, they are equal to each other. That is to say, BQ equals to BS. But we have already found out that BQ equals to 5 units. So we can write here that BQ equals to 5 units. And from this equation, 5 equals to BQ equals to BS. We will derive that BS is also equals to 5 units. Here, BS equals to 5 units. In the next step, we'll join points Q and S together by a straight line. By joining points Q and S, we created here triangle QBS. In triangle QBS, side BS equals to side BQ. They are both equal to 5 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle, there are equal angles. So those two angles that are located in front of equal sides must be equal to each other. So if one angle is alpha, then the other angle must be also equal to alpha because of the fact that they are equal to each other. What is the size of angle SBT? The size of this angle. We know that angle ABC equals to 90 degrees. This angle equals to 90 degrees. This angle equals to 30 degrees. Therefore, this angle must be equal to 90 degrees minus 30 degrees. That is actually 60 degrees. So I found out that this angle equals to 60 degrees. Okay? Angle SBQ equals to 60 degrees. So if we focus on triangle SBQ, this angle equals to 60 degrees, and the sum of the angles in any triangle is 180 degrees. Therefore, if this angle equals to 60 degrees, it means that the other two angles must be equal to 180 degrees minus 60 degrees. 180 degrees minus 60 degrees is 120 degrees. That is to say, alpha plus alpha must be equal to 120 degrees. Here in triangle QBS, in triangle QBS, alpha plus alpha equals to 120 degrees. Okay, so alpha plus alpha is 2 alpha, that is equal to 120 degrees. Here we divide this equation by 2, and we'll get that alpha equals to 120 degrees over 2, it is 60 degrees. So I found out that angle alpha equals to 60 degrees. This is angle alpha that is equal to 60 degrees. And this is also angle alpha that is equal to 60 degrees. So actually, inside triangle QSB, we have 3 angles that are all equal to 60 degrees. Therefore, triangle QBS is an equilateral triangle. Equilateral triangle. Because all of its angles, they are equal to 60 degrees. And because of the fact that triangle QBS is an equilateral triangle, all of its sides, of course, are equal to each other. And we know that side HB equals to 5 units, side BQ equals to 5 units. Therefore, QS must be also equal to 5 units because of the fact that all the sides of the equilateral triangle are equal to each other. So QS is also equal to 5 units. Okay. So in the next step, we will join points O and S together by a straight line. Point O is the center of the circle, point S is the point of the circle itself, therefore OS is the radius of the circle that is equal to R. And again, we have the radius OS that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay, so in the next step, I'll copy quadrilateral SOBQ in a new page and we'll analyze quadrilateral SOBQ. Okay. We have quadrilateral SOBQ. So actually this is quadrilateral SOBQ that I copied from the original drawing. We know that the sum of the angles in any quadrilateral is equal to 360 degrees. That is to say, the sum of those four angles must be equal to 360 degrees. Therefore, 360 degrees minus the sum of the three angles must be equal to the size of the missing angle, this missing angle. So 360 degrees minus 90 degrees minus 90 degrees minus 60 degrees is equal to the missing angle, that is actually angle QOS, is equal to angle QOS. That is to say, 360 degrees minus 90 degrees minus 90 degrees is minus 180 degrees, minus 180 degrees minus 60 degrees is minus 240 degrees. So minus 360 degrees minus 240 degrees, it is equal to 120 degrees. So we found out that the missing angle QOS equals to 120 degrees. Okay, so you can write in the drawing that the missing angle, this is the missing angle that is equal to 120 degrees. Okay, so in the next step I will present to you the law of cosines, and we'll implement the law of cosines in the green triangle QOS. Okay, so what is the law of cosines? The law of cosines is true in any triangle. if we have triangle ABC, that could be any triangle. This is triangle ABC. The length of side AB of this triangle ABC is A units. The length of side AC is B units, and the length of side BC is C units, and the angle between side AB and side AC is theta. Then according to the law of cosines, we get that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Okay. Again, here, this triangle ABC, that could be any triangle. C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. We'll implement the law of cosines in triangle QOS. So I'll copy triangle QOS in new page, and we'll implement the law of cosines in triangle QOS. So this is triangle QOS that I copied from the original drawing. According to the law of cosines, we get that if we implement it into triangle QOS, we get that 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. I repeat again, according to the law of cosines, 5 squared equals to R squared plus R squared minus 2 times R times cosine 120 degrees. 5 squared is 25 degrees. 5 squared is 25, and it is equal to R squared plus R squared is 2R squared minus 2 times R is minus 2R squared. Cosine 120 degrees is minus 1/2, so we substitute cosine 30 degrees by minus 1/2. Here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. Minus and minus is plus. So in conclusion, we found out that according to the law of cosines, 25 equals to 2R squared plus R squared is 3R squared. So here we will divide this equation by 3, and we get that R squared equals to 25 over 3. R squared equals to 25 over 3. And here, so we found out that R squared equals to 25 over 3. We know that the area of the circle is pi R squared. So it is pi times R squared, and R squared is 25 over 3. So in conclusion, we found out that the area of this circle is equals to 25 pi over 3 square units, or in terms of numbers, it is equal to 26.18 square units. Okay, I'll repeat again. we actually found out that the area of the circle, the area that we are looking for, equals to 26.18 square units. Okay. The area of this circle, the area that we are looking for, equals to either 25 pi over 3 square units, or in terms of numbers, is equal to 26.18 square units. We finished with the first question. In the next step, I will present to you the second question, and we'll actually solve the second question in 3 different methods. So, in the drawing, we have a quarter circle. Inside this quarter circle, we have a small circle. It is given us in the question that line segment CD equals to 8 units. It is also given us in the question that angle ACD equals to 90 degrees, and our mission is to find out the value of this green area. So we start with the first method. And in the first method, we define the center of the small circle as point J. We define the point of tendency of tangent CD with the small circle as point E. We define the point of tendency of tangent OB with the small circle as point F. We will join points O and F together. We join points E and J together by straight line. Point J is the center of the circle. Point E is the point of the circle itself. Therefore, JE is the radius of the circle that will be defined as R. So the radius of the small circle is R. Therefore, JE equals to R. And we have the radius JE that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we'll join points J and F together by a straight line. Point J is the center of the circle, point F is the point of the circle itself, therefore JF is the radius of the circle that is equal to R. And again, we have the radius JF that is drawn to the point of tendency, therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. And we also know that according to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus here, AO is the radius of the quarter circle, so we'll define the radius of the quarter circle as capital R. So AO as a radius, it is absolutely a straight line. Okay, so if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees. So this angle equals to 90 degrees, plus the missing angle. In total, they must be equal to 180 degrees. So the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on this side of the straight line AO at point C to 180 degrees. This angle must be equal to 90 degrees. And we also know that this is the center of the quarter circle, and this angle must be equal to 90 degrees. Because of the fact that this is a quarter circle, this angle must be equal to 90 degrees, and this point O must be the center of the quarter circle. Okay. So here, from the center of the small circle, that is to say, from point J, we go perpendicular on CO. Again, from point J, we go perpendicular on CO. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point J and CO as T. So inside quadrilateral TJOF, inside the small quadrilateral TJOF, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. Therefore, the missing angle, the fourth angle, must be also equal to 90 degrees. In order to complete the sum of the angles in the small quadrilateral to 360 degrees, the missing angle must be also equal to 90 degrees. Likewise, we focus on the small quadrilateral CETJ. In this small quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. Therefore, the fourth angle must be also equal to 90 degrees. So I actually found out that angle EJT, this angle is equal to 90 degrees plus 90 degrees is 180 degrees. Angle EJF, this angle EJF equals to 180 degrees. And because of the fact that it is equal to 180 degrees, it means that it's a straight line. So angle EGF is a straight line, and therefore line segment EGF is a straight line. If line segment EJF is a straight line, EF is also a straight line. EF is a straight line. Okay, EF is a straight line. If EF is a straight line, it means that quadrilateral CEOF is a rectangle. Again, quadrilateral CEOF is a rectangle. Why? Because it has 4 right angles. So I write it down. Quadrilateral CEOF, this quadrilateral is a rectangle. Because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. Okay? That is to say, side EF must be equal to side CO. EF equals to CO. But we have already found out that EF equals to R plus R, that is 2R. And from this equation, 2R equals to EF equals to CO, we will derive that CO is also equals to 2R. CO equals to 2R. Here, CO equals to 2R. Okay, so in the next step, we'll join points O and D together by a straight line. Point O is the center of the quarter circle, point D is the point of the quarter circle itself, therefore D is the radius of the quarter circle, that is equal to capital R. Now we will implement the Pythagoras theorem on the green right triangle, triangle ODC. On the green right triangle, triangle ODC, by PT is the relation from Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is OD, therefore the square of the hypotenuse is OD squared, and it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to CO squared plus CD squared. I'll repeat again. In the right green triangle ODC, according to the Pythagoras theorem, OD square equals to CO square plus CD square. OD equals to capital R, therefore OD square is capital R square. That is equal to CO square. CO equals to 2R, therefore CO square equals to 2R square, that is 4R square. Plus CD square. CD equals to 8, according to what is given as the equation, therefore CD square is 8 squared, that is 64. So in conclusion, we found out that according to equation number 1, R square equals capital R square equals to 4R square plus 64. Here we subtract 4R square from this equation number 1, and we get that according to equation number 1, capital R square minus 4R square equals to 64. So we actually found out that according to equation number 1, capital R square minus 4R square equals to 64. What is the area of the green shape? The area of the green shape is equal to the area of the quarter circle minus the area of the small circle. So I write it down. The area of the green shape is equal to the area of the quarter circle minus the area of the small circle. That is to say, the area of the green shape equals to the area of the quarter circle. The area of the quarter circle equals to 4R square, 2 pi R square over 4, when R is equal, R is a capital R actually. So the area of the quarter circle equals to pi capital R square over 4. And the area of the small circle equals to pi R square. R is a small r. So here we will take pi over 4 as a common factor out of those two expressions. So pi over 4 is a common factor. What is left from pi r square over 4 after we took from it pi over 4 as a common factor? What is left is actually r square, capital R square. What is left from minus pi r square after we took from it pi over 4 square? What is left, it's actually minus 4r square. Why? Because minus 4r square times pi over 4 is equal exactly to minus pi r square. Okay, so we found out that the value of the green shape equals to pi over 4 times capital R square minus 4r square. But we have already found out that the value of the expression capital R square minus 4R square equals to 64. That is to say, we can substitute capital R square minus 4R square by 64. So we'll do it now, and we get that here pi over 4, and capital R square minus 4r square equals to 64, so we substitute it by 64, and found out that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so this expression in total equals to 16 pi. Or in terms of numbers, it is equal to 50.265 square units. So I'll repeat again that the area of this green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. We finished with the first method. In the next step I will present to you how to find out the value of this green shape according to the second method. We'll use the things that we have already found out in the first method. We have already found out that CO equals to 2R. Here we have the radius of the small circle, that is R. We have also here the radius of the small circle, that is R. We know that here this angle equals to 90 degrees. We'll complete the quarter circle to a circle. So we completed the quarter circle to a circle. We'll extend the radius AO by straight line until it intersects with the circle at point, and we'll define the intersection point with the extended radius AO in the circle as point M. We'll extend here line segment CD by straight line until it touches the circle, and we'll define the touching point of the extended CD in the circle as point L. We know that AO is the radius of the circle, of the big circle, that is equal to capital R. So AO equals to capital R, CO equals to R, therefore AC equals to AO minus CO. Again, AC equals to AO minus CO. That is to say, is equal to capital R minus 2R. So here we know that AO is the radius of the circle, therefore it is absolutely a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees. So this angle equals to 90 degrees, therefore the missing angle must be also equal to 90 degrees. In order to complete the sum of the angles on this side of the straight line CO at point C to 180 degrees, this angle must be also equal to 90 degrees. Likewise, we extended the straight line CD. We extended this straight line CD by straight line, and when you extend the straight line by straight line, the result DL must be also a straight line. So DL is a straight line. So if we focus on the lower side of the straight line DL, in the lower side at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have at the lower side of LD at point C? We have this angle that is equal to 90 degrees plus this missing angle. So the missing angle must be also equal to 90 degrees in order to complete the sum of the angles in the lower side of LD, on the straight line LD at point C to 180 degrees. This angle must be equal to 90 degrees. Okay, so in the next step, we will join points N, L, and O together by a straight line. Here, point L, point O is the center of the circle, point L is the point of the circle itself, therefore LO is the radius of the circle that is equal to capital R. We join points L and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of the circle, that is the big circle, that is equal to capital R. So in the next step, we will prove that those two right triangles can go into each other. So we prove that the right triangle LOD congruent to the right green triangle COD. So first of all, we have side CO that is a current side, it belongs to both triangles, so CO equals to CO is a current side. CO equals to CO is a current side that belongs to both triangles. Okay, CO equals to CO. In addition, we have side LO equals to side OD. They are both the radii of the circle, therefore they are equal to each other. So LO equals to OD. They are both equal to the radius of the big circle that is equal to capital R. So by proving that the hypotenuse and one perpendicular of the two right triangles can go into each other, we prove that the two right triangles can go into each other. And I'll explain you why. So, because of the fact that if we have right triangle ABC, and the right triangle, this is the right triangle ABC, and we also have another right triangle DEF. So if those two right triangles have the same hypotenuse. For example, both the hypotenuses are equal to 5 units, and we have also one side that is equal to each other. Here side AB equals to side DE equals to 3 units. So they have the hypotenuse is equal in both those two right angles, and also one perpendicular. AB equals to DE equals to 3 units. So the third side must be also equal, according to the Pythagoras theorem. The value of the third side will be equal to the square root of 5 squared minus 3 squared. 5 squared minus 3 squared is 25 minus 16. The square root of 16 is 4. Here also it will be 5 squared minus 3 squared, that is 4. So I found out that if we have two right triangles that have the same hypotenuse and one side it is also congruent, then the third side must also congruent. That is to say, we proved that those two right triangles congruent to each other. Why? Because they have the hypotenuse that are equal in both those two right triangles, and one perpendicular that is also equal to each other. Therefore, the third side must be also equal to each other, and therefore those two right triangles will be congruent to each other according to side rule. So triangle LOD congruent to the right triangle OCD according to side rule. And from the fact that those two right triangles congruent to each other, we derive that DC equals to CL. DC equals to CL. DC equals to CL. DC equals to CL. According to the rule that corresponding here, DC equals to CL. According to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides must be also equal to each other. So DC equals to CL, but DC equals to 8 units according to what is given us in the question. DC equals to 8, and from this equation n equals to DC equals to CL, we derive that CL is also equals to 8 units. Here CL equals to 8 units. So in the next step, so here we know that point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of this circle, that is equal to capital R. So here in the next step we will implement rule number 11 in our drawing. According to rule number 11, according to rule number 11, if we have chord AB that intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay. We can implement rule number 11 in our drawing, because in our drawing we have chord AM intersect with chord DL at point C. So I'll write it down. In our drawing, we have chord AM that intersects with chord LD at point C. Point C is the intersection point. Repeat again. In our drawing, we have chord AM that intersects with chord LD at point C. Therefore, according to rule number 11, we get that DC times CL, DC times CL equals to AC times CM. Repeat again, DC times CL equals to AC times CM. According to rule number 11, we get that DC times CL equals to AC times CM. Okay, so here DC equals to 8 and CL equals to 8 also. So DC times CL is 8 times 8, it is 64. That is equal to AC. What is the value of AC? AC equals to capital R minus 2R. Times CM. What is the value of CM? It's very easy to see from the drawing that CM equals to 2R plus capital R. So in conclusion, we found out that according to rule number 11, 64 equals to capital R minus 2R times R, capital R plus 2R. That is to say, it is equal to capital R minus 2R times capital R plus 2R. So here we use the trigonometric identity, the algebraic identity that A plus B times A minus B equals to A squared minus B squared. In our specific equation, A equals to capital R and B equals to 2R. And here it is equal to A squared minus B squared. So R minus 2R times R plus times R minus 2R times R plus times 2R plus R equals to R capital R squared minus 2R squared. 2R squared is 4R squared. So in conclusion, we found out that 64 equals to capital R squared minus 4R squared. Okay, 64 equals to capital R squared minus 4R squared. And what is the area of the green shape? The area of the green shape is equal to the area of the quarter circle minus the area of the small circle. Repeat again the equation. The area that we are looking for, that is the area of the green shape, equals to the area of the quarter circle minus the area of the small circle. That is to say, the area of the quarter circle equals to pi capital R square over 4 minus the area of the small circle, that is equal to pi R square. Okay. So I found out that the area of the green shape equals to capital to pi times capital R square over 4 minus pi R square. Here we take pi over 4 as a current factor out of those two expressions. So what is left from pi capital R square over 4 after we took from it pi over 4 as a common factor? What is left is actually capital R square. What is left from pi R square after we took from it pi over 4 as a common factor? What is left is actually minus 4R square. Why? Because minus 4R square times pi over 4 equals to exactly to minus pi R square. So I found out that the area of the green shape equals to pi over 4 times capital R square minus 4R square. But we have already found out that the expression capital R square minus 4R square equals to 64. Therefore we can substitute this expression by 64. We'll do it now. We'll get that it is equal to pi over 4 times 64. And 64 over 4 is 16, so this expression in total equals to 16 pi. So we actually found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. Okay, we finished with the second method. In the next step, I'll present to you how to find out the area of the green shape according to the third method. Here we already found out that CO equals to 2R, OC is the radius of the quarter circle that is equal to capital R. Here AC equals to capital R minus 2R. This angle equals to 90 degrees because it is a quarter circle here. In the next step, we will complete the quarter circle to a semicircle. Then we'll extend the radius AO by straight line until it intersects with the semicircle we define the intersection point of the extended radius AO in the semicircle as point M. So here point O is the center of the semicircle, point M is the point of the semicircle itself, therefore OM is the radius of the semicircle that is equal to capital R. So here we extended the radius AO by a straight line. AO is a radius with a straight line, and when you extend a straight line by a straight line, the result AM must be a straight line. So we have here a straight line AM, we have straight line AM that is equal to capital R plus capital R is 2R. Therefore, AM must be the diameter of this semicircle, because AM passes through the center. AM that is equal to 2 times capital R passes through the center of the semicircle. Therefore, any straight line that passes through the center of the semicircle must be the diameter of the semicircle. Therefore, AM that is equal to 2 times capital R, it is the diameter of the semicircle. Because of the fact that AM is a straight line, we can see it as a chord. We can see AM as a chord, and any chord in a circle or in the semicircle that passes through the center of the circle or of the semicircle must be the diameter of the circle. Okay, I repeat again. Chord AM passes through the center of the semicircle, therefore it is the diameter of the semicircle. Okay. So here we will join points M and D together by a straight line. We will join points A and D together by a straight line. What is the definition of angle MDA or angle ADM? What is the definition of angle ADM? Angle ADM is a peripheral angle. Again, angle ADM is a peripheral angle. And this peripheral angle, angle ADM, rests on AM, that is the diameter of the circle. We have peripheral angle ADM that rests on the diameter of the circle, and according to rule number 5, any peripheral angle that rests on the diameter of the circle must be equal to 90 degrees. Here we have peripheral angle ABM that rests on AB, that is the diameter of the circle. Therefore, peripheral angle AMB equals to 90 degrees according to this rule, rule number 5. We can implement rule number 5 in our drawing. Why? Because in our drawing we have peripheral angle ADM that rests on AEM, that is the diameter of this semicircle. Therefore, peripheral angle ADM equals to 90 degrees according to rule number 5. This angle equals to 90 degrees. Because of the fact that it rests on the diameter of the circle. So here, peripheral angle ADM equals to 90 degrees. Peripheral angle ADM is equal to 90 degrees according to rule number 5. We define angle AMD as alpha. We define angle DAM as beta. We'll focus on the right triangle, triangle ADM. On the right triangle, triangle ADM, this angle equals to 90 degrees. Therefore, the rest other two angles, that is to say alpha and beta, in total, they must be equal to 90 degrees also, because 90 degrees plus 90 degrees, it is 180 degrees, that is the sum of the angles in any triangle. That is to say, here we found out that alpha plus beta, in total, they must be equal to 90 degrees. Here, if we subtract beta from this equation, we get that alpha equals to 90 degrees minus beta. And if we subtract alpha from this equation, we will get that beta equals to 90 degrees minus alpha. Okay. We'll focus on the right triangle, triangle CDM. First of all, before we continue, we know that here AM, AO is the radius of this quarter circle, therefore it is absolutely a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have? This side of AO at point C, we have this angle that is equal to 90 degrees. Plus the missing angle, in total they must be equal to 180 degrees, therefore the missing angle must be equal to 90 degrees in order to complete the sum of the angles on this side of the straight line AO at point C to 180 degrees. This angle must be also equal to 90 degrees. So we'll focus on the right triangle, triangle MCD. On this right triangle, this angle equals to alpha. This angle equals to 90 degrees. Therefore, this angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. So we found out that the missing angle here must be equal to 90 degrees minus alpha. But here we found out that 90 degrees minus alpha equals to beta. So we can substitute 90 degrees minus alpha here by beta. Likewise, we'll focus on the right triangle, triangle ACD. In this right triangle, triangle ACD, this angle equals to beta. This angle equals to 90 degrees, therefore the missing angle here must be equal to 90 degrees minus beta. But we have already found out that 90 degrees minus beta equals to alpha. So we substitute here 90 degrees minus beta by alpha. So in the next step, we'll prove that the right green triangle, triangle ACD can go into the right triangle, triangle CMD. So I write it down. Triangle ADC, the right green triangle, is similar to the right triangle, triangle CDM. So why those two triangles, why those two right triangles are similar to each other? First of all, we know that this angle ADC, equals to this angle, that is angle CMD, I'll repeat again, those two angles, they are both equal to alpha, therefore they are equal to each other. In addition, this angle is angle CAD, that is equal to this angle, that is actually angle MDC. Repeat again, those two angles, they are both equal to beta, therefore they are equal to each other. And finally, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. That is to say, angle ACD is equal to angle MCD I repeat again, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So we actually found out that those two right triangles are similar to each other according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that AC over CD is equal to CD over CM. Repeat again. We derive that AC over CD equals to CD over CM. AC equals to capital R minus 2R over CD. CD equals to 8 units, and it is equal to CD, that is 8 units, over CM. What is the value of CM? It is very easy to see from the drawing that CM equals to capital R plus 2R. So we actually found out that according to equation number 1, capital R minus 2R over 8 equals to 8 over capital R plus 2R. Here we cross multiply this equation number 1, and we get that according to equation number 1, 8 times 8 is 64, that is equal to capital R plus 2R times capital R minus 2R. 64 equals to capital R plus 2R times capital R minus 2R. So 64 equals to A plus B times A minus B equals to A squared minus B squared. That is to say, it is equal to capital R squared minus 4R squared. So I found out that according to equation number 1, 64 equals to capital R squared minus 4R squared. So what is the area of the grain shape? We have already found out that the area of the grain shape is equal to the area of the quarter circle minus the area of the small circle. I'll repeat again. The area of the grain shape equals to the area of the quarter circle minus the area of the small circle. So the area of the grain shape equals to the area of the quarter circle, that is pi times capital R square over 4 minus the area of the small circle, that is equal to pi R square. So I found out that the area of the grain shape equals to pi times capital R square minus pi R square. Here we'll take pi over 4 as a common factor out of those two expressions. So what is left from pi R square over 4 after we took from it pi over 4 as a common factor? What is left is actually capital R square. And what is left from minus pi R square after we took from it pi over 4 as a common factor? What is left is actually minus 4 times R square, because of the fact that minus 4R square times pi over 4 equals to exactly to minus pi R square. So here we found out that the area of the grain shape equals to pi over 4 times capital R square minus 4R square. But we have already found out that this expression capital R square minus 4R square equals to 64, therefore we can substitute this expression by 64. We'll do it now, and we get that pi over 4 times 64 is the area of the grain shape. 64 over 4 is 16, so in total this expression equals to 16 pi. So I found out that the area of the grain shape equals to 16 pi square units, or in terms of numbers, it is equal to, it is equal to 50.265 square units. Okay, so we finished with the third method. In the next step, I'll summarize the lecture. We start with the first question, of course. in the drawing we have square ABCD. Inside square ABCD we have a circle. We know that angle CBT equals to 30 degrees. We also know that line segment PD equals to 5 units. Our mission is to find out the area of the circle. I will repeat again. Our mission is to find out the area of this circle that is inside square ABCD. Okay, this is our mission, to find out the area of this circle. Okay, so first of all we defined the center of this circle as O. We joined points O and Q together by a straight line. Point O is the center of the circle, point Q is the point of the circle itself. Therefore, Q is the radius of the circle that is equal to R according to our definition. And we have the radius OQ that is drawn to the point of tendency. Therefore, this angle equals to 90 degrees and this angle equals to 90 degrees according to the rule that the tangent to a circle is perpendicular to the radius drawn to its point of tendency. Likewise, we joined points O and P together by a straight line. Point O is the center of the circle. Point P is the point of the circle itself. Therefore, OP is the radius of the circle that is equal to R. We have the radius OP that is drawn to the point of tendency. Therefore, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees according to rule number 1. We know that all the angles inside the square are right angles. So those 4 angles, they are all right angles. And especially this angle, it is a right angle. So actually inside quadrilateral AQPO, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees plus the size of the 4th angle. In total, they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. 270 degrees plus 90 degrees is 360 degrees. Therefore, this angle must be equal to 90 degrees. In order to complete the sum of the angles in quadrilateral AQPO to 360 degrees, this angle must be equal to 90 degrees. So we actually found out that inside quadrilateral AQPO we have 4 right angles. Therefore, we will relate to quadrilateral AQPO as a rectangle. Here, quadrilateral AQPO, that is 4 right angles, is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, AQ equals to PO. But we have already found out that PO equals to R. So we can write here that PO equals to R. And from this equation, R equals to PO equals to AQ, we'll derive that AQ is also equals to R. AQ is also equals to R. Here, AQ equals to R. Likewise, according to the sum rule that the opposite sides of a rectangle are equal to each other, we get that QO equals to AP. QO equals to AP, but we have already found out that QO equals to R. And from this equation, R equals to QO equals to AP, we derive that AP is also equals to R. Here, AP equals to R, therefore, we actually found out that quadrilateral AQPO is not a rectangle but a square because all of its sides are equal to each other, they are equal to R. Okay? And we also know that all the sides of square ABCD must be equal to each other. That is to say, here, side AD must be equal to side AB in square ABCD. Side AD equals to side AB in square ABCD. What is the value of AD? AD equals to 5 plus R. What is the value of AB? The value of AB is R plus QB. AB equals to R plus QB. Here we subtracted R from this equation, equation number 1. So R will get cancelled, and we found out that BQ equals to 5. Here, BQ equals to 5 units. Then I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common standpoint to a circle are equal. If we have the common standpoint point P, from the common standpoint point P, we have tangent PA and tangent PB, and according to this rule, rule number 2, PA equals to PB. So we can implement rule number 2 in our drawing because we have the common standpoint point B. From the common standpoint point B, we have tangent BQ and tangent BS. And according to rule number 2, they are equal to each other. That is to say, BQ equals to BS according to rule number 2, but we have already found out that BQ equals to 5 units, so we can write here that BQ equals to 5, and from this equation 5 equals to BQ equals to BS, we derive that BS is also equals to 5 units. Here BS equals to 5 units. Then we join points Q and S together by a straight line. In this way we got triangle QBS. This is triangle QBS. In triangle QBS, what is the size of this angle? Angle ABQ. Angle ABQ will be equal to angle ABC equals to 90 degrees. This angle equals to 30 degrees. So 90 degrees minus 30 degrees will be equal to this angle. Very simple. That is to say 90 degrees minus 30 degrees is 60 degrees. So this angle equals to 60 degrees. Okay? And in triangle SBQ, those two sides are equal to each other. They are both equal to 5 units, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle, there are equal angles. So those two angles that are located in front of equal sides must be equal to each other. So if one angle is alpha, then the other angle must be also equal to alpha because of the fact that they are equal to each other. This angle equals to 60 degrees. Therefore, the other two angles must be equal to 180 degrees minus 60 degrees, that is 120 degrees. That is to say, alpha plus alpha must be equal to 120 degrees. In triangle QBS, alpha plus alpha must be equal to 120 degrees. Alpha plus alpha is 2 alpha, that is equal to 120 degrees. We divided this equation by 2 and found out that alpha equals to 120 degrees over 2, that is 60 degrees. So here, this is angle alpha that is equal to 60 degrees, and this is also angle alpha that is also equal to 60 degrees. So we actually found out that inside triangle QBS we have three angles that are all equal to 60 degrees. Therefore, triangle QBS is an equilateral triangle. Why? Because all of its angles are equal to 60 degrees. Yes, triangle QBS is an equilateral triangle. And because of the fact that triangle QBS is an equilateral triangle, it means that all of its sides are equal to each other. Side QB equals to 5 units, side BS equals to 5 units, therefore the missing side, side QS, must be also equal to 5 units. So here QS equals to 5 units. Okay, then I copied quadrilateral QBSO in a new page and we analyze triangle quadrilateral QBOS. This is quadrilateral QBOS that I copied from the original drawing. This angle equals to 90 degrees. Here, actually, we have point Q, we have here QS, and we actually joined here points O and S together by a straight line. Point O is the center of the circle, point S is the point of the circle itself, therefore OS is the radius of the circle that is equal to R. We have the radius OS that is drawn to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. So I found out that this angle equals to 90 degrees, this angle is also equals to 90 degrees according to rule number 1, and we just right now found out that this angle equals to 60 degrees. And we know that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore 360 degrees minus the sum of those three angles must be equal to the size of the missing angle, that is this angle. That is to say, 360 degrees minus 90 degrees minus 90 degrees minus 60 degrees must be equal to the size of this angle. That is angle SOQ. So 360 degrees minus 90 degrees minus 60 degrees is 360 degrees minus 240 degrees, that is 120 degrees. So we found out that the missing angle equals to 120 degrees. This is the missing angle that is equal to 120 degrees. Then I presented to you the law of cosines, and we implemented the law of cosines in this green triangle, triangle QOS. What is the law of cosines? The law of cosines is true in any triangle. So here we have triangle ABC that could be any triangle. Side AB equals to A units, side AC equals to B units, and side BC equals to C units in its length. And the angle between side AB and side AC is theta. So here, according to the law of cosines, we get that C square equals to A square plus B square minus 2 times A times B times cosine theta. Okay, again, C square equals to A square plus B square minus 2 times A times B times cosine theta. We actually implemented the law of cosines in the green triangle, triangle QOC. So I copied triangle QOC in this new page, and we implemented the law of cosines in this triangle, triangle QOS. This angle equals to 180 degrees. QO equals to R, and OS also equals to R, and QS equals to 5. According to the law of cosines, we get that 5 square equals to R square plus R square minus 2 times R times cosine 120 degrees. Okay, so 5 square is 25, R square plus R square is 2R square, and here we have 2 times R, that is minus 2R square, and cosine 120 degrees is minus 1 half. Okay, so we have 2 in the denominator and 2 in the denominator, so 2 will get cancelled. Minus and minus is plus. So in conclusion, we found out that 25 equals to 2R square plus R square, that is 3R square. So 25 equals to 3R square. We divided this equation by 3 and found out that R square equals to 25 over 3. And the radius of the circle is pi R square, of course, but we have already found out that R square equals to 25 over 3. So here we can substitute R square in this equation by 25 over 3. We did it when we got that pi R square equals to pi times 25 over 3. So in conclusion, we found out that the area of the circle equals to either 25 pi over 3 square units, or in terms of numbers, it is equal to 26.18 square units. We finished with the first question, then I presented to you the second question, and we solved the second question in 3 different methods. So in the drawing we have a quarter circle. Inside the quarter circle we have a small circle. We know that line segment CD equals to 8 units, angle ACB equals to 90 degrees, and our mission is to find out the value of the green area. So we define the center of the small circle as J. We join point J and D together by a straight line. JE, point J is the center of the circle, point E is the point of the circle itself, therefore JE is the radius of the circle that is equal to R. We have the radius JE that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle equals also to 90 degrees. Then we join point J and F together by a straight line. Point J is the center of the circle, point F is the point of the circle itself, therefore JF is the radius of the circle, and the small circle that is equal to R. We have the radius JF that is going to the point of tendency, therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. This is a quarter circle, therefore point O is the center of the quarter circle. This angle equals to 90 degrees, and here AO is the radius of the quarter circle that we defined as capital R. It is given as the equation that this angle equals to 90 degrees. AO is the radius of the circle, of the quarter circle, therefore it is absolutely, it's a radius, it is absolutely a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees according to rule number 3. This angle equals to 90 degrees, therefore the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on this side of AO, point C to 180 degrees, this angle must be equal to 90 degrees. Okay, then from the center of the small circle, that is to say from point J, we do perpendicular on CO. So this angle equals to 90 degrees, and this angle equals to 90 degrees according to our construction. Therefore, inside quadrilateral TJOF, we have 1, 2, 3 right angles. Therefore, the fourth angle must be also equal to 90 degrees. Likewise, inside quadrilateral CEJT, we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So we found out that angle EJT, this angle equals to 90 degrees plus 90 degrees, that is 180 degrees. So if angle EJT, this angle equals to 180 degrees, it means that angle EJT is a straight line. If angle EJT is a straight line, then line segment EJT is a straight line, line segment EJF is a straight line, and if line segment EJF is a straight line, it means that EF is also a straight line. If EF is a straight line, it means that quadrilateral CEOF is a triangle. Why? Because it has 4 right angles. So quadrilateral CEOF is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, EF equals to CO. EF equals to CO. But we know that EF equals to R plus R, that is 2R. And from this equation, 2R equals to EF equals to CO, we will derive that CO is also equals to 2R. Here CO equals to 2R. Then we join points O and D together by a straight line. Point O is the center of the quarter circle. Point D is the point of the quarter circle itself, therefore D is the radius of the quarter circle, that is equal to capital R. Then we implemented the Pythagoras theorem on the right green triangle, triangle ODC. In the right green triangle, triangle ODC, according to the Pythagoras theorem, OD square equals to OC square plus CD square. OD square equals to CO square plus CD square. OD is capital R, therefore OD square is capital R square, and it is equal to CO square. CO equals to 2R, therefore CO square is 2R square, that is 4R square, plus CD square. CD is 8, therefore CD square is 8 square, that is 64. So in conclusion, we found out that according to equation number 1, R square equals to 4R square plus 64. Here we subtracted 4R square from this equation number 1, and we found out that according to equation number 1, capital R square minus 4R square equals to 64. Then, what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. Again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle equals to pi times capital R square over 4 minus the area of the small circle, that is pi R square. Here we took pi over 4 as a common factor out of those two expressions. So what is left from pi times capital R square over 4 after we took from it pi over 4 as a common factor? What is left is actually capital R square. What is left from minus pi R square after we took from it pi over 4 as a common factor, what is left is actually minus 4 r square. Why? Because minus 4 r square times pi over 4 equals to exactly to minus pi r square. So in conclusion, we found out that the area of the green shape equals to pi over 4 times capital R square minus 4r square. But this expression, capital R square minus 4r square, capital R square minus 4r square is equal to 64. That is to say, we can substitute this expression by 64. We did it, and we got that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So in conclusion, we found out that the area of the green shape equals to either 16 pi square units, so in terms of numbers, it is equal to 50.2550 to 50.265 units. We finished with the first method. Then I presented to you how to find out the area of the green shape according to the second method. In the second method, here we have already found out that in the first method that CO equals to 2R. So, and here this angle equals to 90 degrees. Therefore, according to rule number 3, this angle must be also equal to 90 degrees. So here LD, actually we completed the quarter circle to a circle, and we extended the radius AO by straight line until it touches the circle at point M. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle, of the big circle, that is equal to capital R. We extended the straight line DC by straight line until it touches the circle at point L. So here then we prove that those two right triangles can go into each other. Again, this angle equals to 90 degrees according to rule number 3, and we have DC is a straight line. We extended the straight line DC by straight line. The result DL must be also a straight line. So if we focus on the lower side of DL at point C, this angle equals to 90 degrees. So the missing angle must be also equal to 90 degrees according to the rule that the sum of the angles on one side of the straight line equals to 180 degrees. So those two triangles are right triangles. We proved that those two triangles can go into each other. Why they can go into each other? Because CO is a common side that belongs to both triangles. Here we join points O and D together by straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of the circle. The big circle is equal to capital R. Point O is the center of the circle, point L is the point of the circle itself, therefore OL is also the radius of the big circle that is equal to capital R. So here OD equals to OL, they are both the area of the circle, therefore they are equal to each other. So we found out that one of the hypotenuse of both those two right triangles and one perpendicular are equal in those two right triangles. Therefore, we actually proved that those two right triangles can go into each other. Why? Because I'll explain you why. Because if we have those two right triangles that have the hypotenuse and one side are equal in both those two right triangles, AC equals to DF equals to 5 and AB equals to DE equals to 3. Therefore, the missing side, the third side, must be also equal in both those two right triangles according to the Pythagoras theorem. Okay? So when we prove that the hypotenuse and one perpendicular in those two right triangles can go into each other, therefore the third side must be also congruent. And because of those facts, actually we proved that the two right triangles can go into each other according to side rule. And from the fact that those two right angles can go into each other, we derive that CD equals to LC. CD equals to LC, but CD equals to 8 units according to what is given as the equation. And from this equation, 8 equals to CD equals to CL, we derive that CL is also equals to 8 units. Okay, then I presented to you rule number 11, implemented rule number 11 in our drawing. If we have chord AB that intersects with chord CD at point O, then AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. In our drawing, we have chord AM that intersects with chord LD at point C. Again, chord AM intersects with chord LD at point C. Therefore, according to rule number 11, LC times CD equals to AC times CM. CD times CL equals to AC times CM. CD equals to 8, CL equals to 8, therefore 8 times S is 64. AC equals to capital R minus 2. CM equals to capital R plus 2. Therefore we found out that 64 equals to capital R minus 2R times capital R plus 2R, that is actually equals to capital R square minus 4R square. So in conclusion, we found out that 64 equals to capital R square minus 4R square. And what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle is pi capital R square over 4 minus the area of the circle, that is pi R square. Here we took pi over 4 as a common factor from this expression, and we got that pi over 4 times R square minus 4R square equals to, here, we only found out that capital R square minus 4R square equals to 64, therefore we substituted capital R square minus 4R square by 64, and we found out that the area of the green shape equals to pi times 64 over 4. 64 over 4 is 16, so in conclusion we found out that the area of the green shape equals to 16 pi. On terms of numbers, it is equal to 50.265 square units. Then I presented to you the third method. In the third method, we completed the quarter circle to a semicircle. CO equals to 2R according to the first method. We join points M and D together by a straight line. We join points D and A together by a straight line. In this way we created peripheral angle ADM. Here we extended AO by straight line. Therefore AM, when you extend the straight line by straight line, the result is the straight line. AM is a chord that passes through the center of the circle, and it is equal to 2R, therefore AM is the diameter of this circle. We have chord AD that rests on the diameter of the circle, therefore according to rule number 5 is equal to 90 degrees. We define this angle as alpha, this angle as beta, and here alpha plus beta must be equal to 90 degrees because this angle equals to 90 degrees. If alpha plus beta equals to 90 degrees, it means that alpha equals to 90 degrees minus beta, and beta equals to 90 degrees minus alpha. So in the right triangle MDC, we have this angle that is equal to alpha. This angle equals to 90 degrees, therefore this angle must be equal to 90 degrees minus alpha, but 90 degrees minus alpha is beta, so here we substitute 90 degrees minus alpha by beta. In the right triangle ACD, this angle equals to 90 degrees. This angle equals to beta, therefore this angle must be equal to 90 degrees minus beta, and here it is equal to alpha. So we substitute 90 degrees minus beta by alpha. Then we proved that those two right triangles are similar to each other. Why they are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to beta, therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees, therefore they are equal to each other. So we found out that those two right triangles can go into each other, similar to each other according to angle similarity rule. From the fact that they are similar to each other, we will derive that AC over CD equals to CD over CM. AC equals to capital R minus 2R, CD is 8, so CD is 8 and CM is capital R plus 2R. We cross multiply this equation and found out that 64 equals to capital R plus 2R times capital R minus 2R, that is capital R square minus 4R square. So 64 equals to capital R square minus 4R square. And what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle equals to pi times capital R square over 4, and the area of the small circle equals to pi R square. Here we took pi over 4 as a common factor out of those two expressions. Inside the brackets we left with capital R square minus 4R square. But we have only found out that capital R square minus 4R square equals to 64, therefore we can substitute this expression by 64. We did it, we got that in total that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16. So in conclusion, we found out that the area of the green shape equals to either 16 pi, or in terms of numbers, it is equal to 50.265 units. So in both methods, in all the three methods, we found that the area of the this green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. Okay, thank you very much.